Happy learning! Today we're going to talk about Eulerization. Okay, so we've seen that some graphs don't contain Euler circuits and they don't contain Euler trails. But we may have situations where we want to travel along each edge, basically with as few repeats as possible. So we're going to talk about how to do that today. So what we're going to do today is we will look at how to adjust a graph to ensure that an Euler circuit or trail can be found. Right, for instance, suppose you're delivering a bunch of mail and these edges represent roads. Right, if you want to deliver mail to all the homes, you need to make sure you travel on each edge. So we're going to talk about how to do that today. All right, so this section is called Eulerization, so let's define what Eulerization is. So given a connected graph so this notation here, G equals VE, just saying we have a graph with some vertices and some edges. All right, we're going to make some tweaks to the edge set here, but we're going to keep the vertices the same. So it's hopefully by the end of this definition, it's clear why we have to kind of be careful here. In Eulerization, okay, Microsoft, for whatever reason, doesn't recognize this as a word. So if you type it in Word, it's going to put a little red line under it. But it's a word. All right, Eulerization of G is a new graph okay? This new graph, G prime, it too has a vertex set, the same exact vertex set as our original graph. So we're adding no new vertices, and we're going to have a slightly different edge set. All right, and so we're going to talk about what types of edges we're allowed to add to our edge set. So that okay, the first condition is G prime is obtained from G. So we start with G, and we're going to duplicate some of the edges. All right, so we're going to duplicate some of the edges of G. We can't add any other ones. They have to be duplications. And then the second condition, every vertex of G prime is even. Okay, so we're going to duplicate edges in G to make a new graph where every vertex is even. Then we know we could find an Euler circuit, an Eulerian circuit. A semi-Eulerization is the same as an Eulerization, but we're going to have two odd vertices at the end. All right, so there's going to, when we semi-Eulerize the graph, there's going to still be two odd vertices at the end. That means we're going to have an Euler trail as opposed to an Euler circuit. Okay, so let me give you an example. So suppose our graph is this. Okay, this graph may look familiar to you. This is the Königsberg Bridge map, right? That's the question that started this whole field, the Königsberg Bridge problem. All right, and if we want to Eulerize this graph, basically what we want to do is duplicate some of these edges so that we end up with only even degrees at the end. All right, and so right now we have odd degree, odd, odd, and odd. If we add that edge, now we have even, even, odd, odd, and maybe we duplicate one of those edges. And so this is an Eulerization. But if we did the same thing, so we're looking at the same graph, and let's say I duplicated this edge. Okay, so even, even. These two are odd. If I put an edge here, this is not duplicating one of the old edges. This is a totally new edge. Okay, so this is not an Eulerization. All right, you see that? You have to duplicate edges that already existed. If you wanted to do something like this, we could duplicate two edges to do that, but we can't just do this one bigger edge. All right, so you could picture, like in Eulerization, if these edges represent bridges, it's just we're going to walk on one of the bridges twice. This would be like I'm going to build a new bridge, which is expensive, so we're not doing that. Okay, so let's talk about how to Eulerize a graph. Guessing and checking is not really a great strategy in general, so we're going to have some techniques. Okay, this is very simple. First step, we're going to identify odd vertices. All right, so we'll start, we have our graph. We're going to find the degree of each of the vertices and just figure out which ones are odd. Okay, step 2 is we are going to pair up nearby odd vertices. Okay, what does nearby means? I don't really know. It means whatever you want it to mean. So like these two vertices are close to each other on the graph, so we could pair them up. But we'll be more precise with nearby in a second. That's why I was kind of joking with saying I don't really know. We'll be more precise. We're going to start identifying some weights or lengths to these edges. So then we'll actually have a way to define what nearby means. And so then the final step is we're going to duplicate edges along a path from one vertex to its pair. All right, it's really as simple as that. So let's look at an example. So the example is that there's a night watch in this small town that's just going to walk around the neighborhood, make sure that there's no, teenagers causing problems. And this is what the small town's roads look like. So each vertex represents an intersection, and each edge represents a road. All right, and so this Good Samaritan is going to basically walk around the neighborhood to make sure nobody's causing trouble. Okay? And so what we want to do is we don't want this person to have to duplicate the same edge over and over and over again. We want to find just a nice Eulerian circuit that this person could walk every night to see all of the different roads. All right, so we need to Eulerize this graph. And so how do we do that? We need to identify the odd vertices. Let's find the odd vertices. The degree of this vertex is 4. The degree of this vertex is 2. Remember, the degree is like the number of edges out of the vertex. The degree of this bad boy here, of course, that's 3. All right, we have an odd vertex. This one is 3. This one is 3. This one is 3. We have 4 odd vertices here. Maybe there's more. 2, 4, 2, 2, and 4. All right, so to Eulerize this graph, we look at our odd vertices and we pair them up. And so there's a bunch of different ways to pair them up. But one such way is we could pair these two up, and we could pair these two up. Duplicate edges along a path from one vertex to its pair. Let's duplicate this edge. And we'll duplicate that edge. Okay? Now we could check. This edge now has a degree of 4. This one has a degree of 4. This has a degree of 4 and 4. We have no odd vertices, so we have an Eulerian graph. And so we could use some of the algorithms that we discussed in the previous video to find an Eulerian circuit on this graph. Okay, but what you might notice is you might be interested in is like maybe there could be a graph that has like an odd number of odd vertices. Right? Then how would you pair them up? Right? Let's say there was 3 odd vertices. How would you pair it up? Well, it turns out it's impossible for there to be an odd number of odd vertices. And so that's going to be, we're going to see that in the following theorem. This is called the handshaking lemma. Okay, what does it say? It says the sum of the degrees of the vertices equals twice the number of edges. Okay, so I know what you're thinking. What does this have to do with handshaking? And also, how does this tell us that there can't be an odd number of odd vertices? Well, I'll tell you in a second, but let me rewrite this. Instead of in words, we could write this mathematically. This is saying that the degree of the first vertex plus the degree of the second vertex plus the degree of, let's say, the nth vertex is equal to twice the number of edges. And here this absolute value bar just denotes like the size of the number of edges, like just the total, you count the number of edges. Okay? And so this here, 2 times some number is even. Right? 2 times any whole number is even. So the left-hand side equals an even number. So we need the left-hand side to be even. If there were an odd number of odd vertices, this left-hand side would be odd. And an odd can't equal an even. So we must have an even number of odd vertices, right? So this has to be even as well, right? If two numbers are equal, they have to have the same parity. And so we can't have an odd number of odd vertices. So it's always possible. What's the point? It's always possible to pair them up. If you're concerned, no need to be concerned. Okay, what does this have to do with handshaking? You could imagine that if you are at a party and you're shaking a bunch of hands, you could make a graph where the vertices represent you and the partygoers, and the edges represent whether or not you shook hands. Okay? And this says that basically the degree of a vertex is the number of people you shook hands with. Okay? And so it's the total number of handshakes. It's the total number of each person's handshakes, which would be, so the number of edges is the total number of handshakes. So if you double the number of handshakes, you get all of the degrees. That's why it's called the handshake lemma. It's not really important. Okay, but what is important is we're always going to have an even number of odd vertices. Okay, so a corollary, so cor means corollary. It follows immediately from the theorem. There must be an even number of odd vertices. Okay, and try it on your own. Just draw some graphs. See if you could make a graph with an odd number of odd vertices. It's impossible. Okay, and so what we're going to look at now is we're going to look at this example, but we're going to assign some lengths to the edges. Right? This is somebody walking around their neighborhood. These roads should have some lengths to them. And we're going to try to duplicate edges that have small weights. We don't want to duplicate these mile-long roads because then our patrol person is going to get tired. This is called, what we're going to do now is called the Chinese postman problem. Okay? It was a mathematician in China by the name of Meiku Quan in the 60s asked this question, and we call it the Chinese postman problem. Basically, how to duplicate the edges as cheaply as possible. We need a little bit of notation before we could actually get to trying to solve this problem. In general, the problem is very hard, but we'll have some general techniques. Okay, so we've been looking at graphs so far. A weighted graph all right, what is a weighted graph? Well, it has a vertex set, it has an edge set, and then it also has a weight, which that's the Greek letter omega, but it looks like a W, so you can just write W. So a weighted graph, G of VE omega, is a graph where each of the edges has a number associated to it. Okay, so we're going to put numbers on the edges, and it typically represents lengths or time it takes to travel along the edge, or maybe the cost if there were toll bridges, right? Some cities have tolls for their bridges, and so we could represent the weight would be like the cost to travel along the bridge. So the number, this number, is the weight. All right, and we write omega of xy, or w of xy, to be the weight of the edge. Okay, and so let's look at that same graph that I just erased, but now with some weights. Okay, so this has length 20. Maybe this is minutes. So maybe this is a very curvy road, and the edge we drew just doesn't capture its geometry. And this is more of a straight shot. So it has 10. Oops. All right, so here is our graph. I'm still putting it together. Okay, so sorry that took a second, but here are the weights on our graph. All right, so these numbers represent the time it takes for this patrol person to walk along the edge. Okay, and so we want to Eulerize this graph. All right, this is an example. We want to Eulerize this graph as cheaply as possible. Right, that's solving the Chinese postman problem, is Eulerizing this graph as cheaply as possible. And so if we use the same Eulerization as we did a few minutes ago, we would double up this edge, and we doubled up this edge. That had a total weight of 12 plus 6, 18. So it's 18 additional minutes if we did this edge and this edge. And so the question is, can we do better than 18? All right, so try to Eulerize this graph and use less than 18 additional weight. Right, so if we did this edge and this one, right, that would give us 12 plus 6 is 18. We want to do better than that. Maybe it's impossible to do better. Okay? And so give it a second, and then I'll show you a better path. Okay, welcome back. So remember, we want to pair up this vertex, this one, and this one. We tried pairing up this and these two, and we got an additional 18. Let's now pair up these two and these two. All right, if we pair up these two, we get an additional weight of 2, and then an additional weight of 3 plus 10. So we get a weight of 2 plus 3 plus 10. That's 15, which is much better than the 18. All right, and maybe it's possible if we go way out of the way to find something a little bit better, but it turns out it's not. This was the best we could do. But we'll see down the line some algorithms to help us find optimal ways to Eulerize a graph when we have weights. But in general, it's a pretty tough problem. Okay? So, yep, that's how you Eulerize a graph, and this is a weighted graph. So weighted graphs are going to be a main character in the videos to come. All right? So I look forward to hearing any comments you have down in the comments, and I will see you next time. Take care. Bye-bye.